be talking about precision measurements with nuclear spin ensembles.
Okay. Thank you very much, Professor Unnikrishnan. And hello, everyone. First of all, let me begin with thanking organizers, Subhadeep, Kasturi, and others. So it was very illuminating meeting for me yesterday and day before. So very nice lectures. Thanks. I thank all the lecturers yesterday and day before. Today I'll be speaking about precision measurements with nuclear spin ensembles. Less precisely about precision, it's more about other aspects. Using NMR technique, as Professor Unnikrishnan mentioned. So we take nuclear spin ensembles and then do magnetic resonance. So the setup is like this. So this is the overall summary of the platform that I'm going to talk about. So we have a bulk sample. It's about 0.5 milliliter of sample. It can be usually liquids. It can be liquid crystal, or it can be even solid. So that is the sample here. And that is placed in very strong magnet of the order of 10 to 20 Tesla. So that's a superconducting magnet. That's a fixed field. And so there is a Helmholtz coil here that is to introduce radio waves or receive the signal, which is also radio wave. Now the sample consists of atoms and molecules, and in each atom there is a nucleus, and this nucleus can be having spin. Spin can be anything. It can be half or 1, 1.5, 2, up to 9/2. So there are different isotopes with various spin numbers. Now, if it is spin half, it's a qubit. Now, if the magnetic field is applied, so that's the 10 to 20 Tesla magnetic field, then we have the Zeeman energy gap. So there is a Zeeman interaction between the nuclear spin and the magnetic field. And so we have energy gap of about 10 to 20 micro electron volt. So that happens to be in the radio wave. So we have hundreds of megahertz energy gap here. So what we do is now send the radio wave, the resonant radio wave, and create superposition between these spin states. So that is the big strength of NMR. So we can do it very precisely. We can create superpositions, very intricate superpositions, and in a controlled manner, and sustain the superpositions for a long time. So that's the big strength of NMR. And then these superpositions, they also induce a signal in the electromagnetic, they induce electromagnetic induction in this coil, and that is recorded as NMR signal. Basically, it comes out as EMF. And that is amplified and recorded as NMR signal, which we can analyze. So that's the entire summary of the platform. Now, what kind of registers? So earlier I showed one spin. So that's one spin, but we can take collection of them. So here, all these are carbon-13 isotopes. So they are all spin half, and there are 3 nitrogens. So they are also N15 isotopes. So they are also spin half. And then we have hydrogens. They are also spin half. So we have 12 qubits here. So we can have another system with 12 qubits, and they're all interacting. They're all addressable. So they all have different resonance frequencies. We can control individually, or we can control collectively. In this example, recently we have come up with 38 qubits. So here there is a semi-addressability. These two silicon we can address separately, but hydrogens are addressed globally. So that is sufficient for certain types of applications. I'll give some more examples later on. So in this system, we could study the charging and discharging of quantum battery. Okay, so this is one example of how intricate quantum control we can achieve. So this is a 12 qubit system, and we have controls on each of the spin and individually and address separately. So we can apply various types of rotations in a very controlled phase as well as duration. And so we can entangle them, and we can study various properties. And this is one algorithm called quantum benchmarking algorithm. So with this platform, we also have a small nitrogen vacancy center platform. So there were two beautiful lectures on NV Center, so I'll not go into the details. Today, I'll be mostly focusing on NMR. So in some sense, they are complementary to each other. NMR lacks the initial pure states, and that is what is the strength of NV Center, but NMR still possesses higher strength in quantum control. So in that sense, there are two complementary architectures, and with them we do quantum control, we do quantum information, we study quantum simulations and quantum transport, and we also are interested in studying some aspects of quantum foundations and a little bit of machine learning and so on. So that's the research program in our lab, and so we call this as a quantum workshop. Okay, just to give a quick comparison between different platforms, we today have classical computers, classical registers. They have very good purity. In fact, they are completely pure. But then they don't have quantum superpositions. And despite having non-local gates and good purity, they don't have any quantum resource. NMR registers, on the other hand, they don't have good state purity, but they have quantum superposition as well as non-local gates. And so they possess a quantum resource called quantum discord. And NV centers, for example, they can provide very good purity, and then we can create quantum superpositions and non-local gates, and so we can demonstrate quantum entanglement. Okay, so coming to the main topic of today's talk. So this is about measurement, and I'm going to categorize the strengths into three categories. So one is using correlated spin network. So how to enhance measurements using correlated spin network, so which is often called as space resource. The other one is called the time resource, using coherences which can be sustained for a long time, as the previous speaker mentioned. The sensitivity or the error is inversely proportional to the time during which you can sustain the coherence. And so that is the time resource. In fact, in this meeting, I think space resource is not as much appreciated as time resource. So I'm going to spend more on the space resource. One can think of combining these two, that you can have the correlations which are long-lived. So that is like having both space and time resource. Okay, so let's start with space resource. See, we got into this motivated by two papers. One is by David Corey in 2005, where he discussed entanglement-assisted metrology. So what he described was, instead of taking one spin and trying to do a measurement, why don't you take a large number of spins and entangle them, and then basically prepare a cat state and then use that for measurements. So this is very interesting. And what you can notice here is the first two qubits require addressability because they have different operations, but all these other qubits, they don't require addressability. So they are all having same operations performed on them. So you can do it in a global way. So that's what is done by Jonathan Jones at Oxford in 2009. So he took this kind of system. So advantage of this kind of system is we can, okay, I'll describe more in the next slide. So they come with certain advantages. So you have a completely addressable central spin surrounded by a large number of identical spins, and they're all coupled to the central spin. So we call the central spin and satellite spins. Now, satellite spins themselves are not interacting with one another. So this is called a star topology system. Now, if you have star topology system, then you can do this kind of operation and create cat state. In this case, they name that as noon state. So I'll explain why it is called noon state. And then they described using noon state, they can beat the standard quantum limit and they can reach towards the Heisenberg limit. So that was very interesting. And we also recognized many of the advantages of these star topology systems, because the central spin is addressable. We can apply any operation like Hadamard gate or whatever gate you want. And then suppose you apply a C0 gate on the satellite qubits. Now one C0 gate simultaneously acts on all the gates because they are all identical. They are all indistinguishable. So there is a massive parallelism going on here. So that is very, in terms of expense, in terms of cost of quantum information, this is least expensive, because one gate does complete entanglement of all the whole system. And here there are n number of spins in zero state, n number of spins in zero state, and zero number of spins in zero state. So that is why it is called noon state. So that's the so zero number of spins in zero state and n number of spins in one state. So that's the nomenclature. So it's called as noon state. Okay, so this is a cat state, and we can create easily large entangled states and no spectral crowding because they're all identical. All the spectral peaks overlap, so there is no spectral crowding. And they allow very precise quantum control. Of course, there is a global control on A spin, and there is a addressable control on the C spin. Now, they also possess a long memory. I'll show some examples. And it can have number of applications, including sensing. Now, just to give a little bit more introduction to the states that we can prepare. So we can identify different states with something called quantum number. So if it is 0, 0 plus 1, 1 by root 2, then 0 has this m equal to plus half. 1 is corresponding to m equal to minus half. So you can add the quantum numbers. So 0 that is plus half, 0 that is plus half, and that is 1, and this 1, 1 that is minus half, minus half. So the difference in quantum numbers, so of the states in the superposition, that is called the quantum number of the coherence, and that is 2 here. Or if you have 0, 1 and 1, 0 by root 2, and then the difference in the quantum numbers is 0, and that is the order of the coherence. Okay, so now we can prepare various orders of coherence. If you have n spins, so we can have various orders of coherence, and that goes as the intensity of those coherences goes as Pascal triangle here. So it depends on how many spins you have and how long you interact, what kind of gate you apply. You can prepare all these different coherences very easily. So in fact, you can have different types of states. You have known states, you have something called MSSM states, you have something called zero quantum states, and zero quantum states, they live very long time. So I'll show you some examples that can be very useful for sensing. So we have various systems of star topologies. So you can have a number of systems. We have now up to 50 plus spin systems in star topology. Okay, so now the idea is like this. So it has 3 steps basically. So you first prepare the known state. It is the space resource. You correlate all the spins. So that is the also called as multiple quantum coherence. So you can prepare any state of given coherence order, quantum coherence order, QH, and then you can detect at the end. So that is, I'll not go into the NMR technicalities of this. You can detect selectively which coherence you want to detect. You can filter out other coherences, and you can detect selectively the coherence order of that you are interested in. In between, you can put all the talks that you want. You can utilize this coherence. You can put sensing, you can put algorithmic cooling, you can put quantum computation, whatever you want in between. So that is the utilization part. Okay, I'll give some examples. So this is the NMR pulse sequence. So that translates into radio waves. So we have some 90-degree pulses, 90 Y pulse, X pulse, and so on. Okay, so that can be converted into NMR pulse sequence. Now, just to give one example, how to use this in measurement. So let us say, let's start with understanding Z noise with this method. So in addition to the Zeeman Hamiltonian, we have the noise Hamiltonian now. So this is again having the same direction. The noise is having the same direction as the Zeeman field. So that's why it is called as Z noise. And this is time dependent noise. So now we can calculate what is the density matrix, how the density matrix evolves with such kind of Hamiltonian. And what happens is the diagonal elements are unaffected by the Z noise. The off diagonal elements decay with this decay constant. And the decay goes like this. It is depends on two factors. One is the noise spectral density, S of omega. So how strong is the noise? Okay, so that what is the color of the noise and so on. So that is captured in this noise spectral density, and then there is a sinc function here. Now again, so you have the induced EMF in the coil, and then that leads to see this decay leads to decay in the signal, and that's why the signal decays, and that erases the quantum memory. So basically, it's called dephasing or incoherence. Now, so how do we suppress this? Okay, this is just one example. It is called Hahn-Echo. It's a very powerful method. It's a very simple but powerful method. Suppose that there are three spins. Initially, they are phase coherent. And now what happens is due to this Z noise, the red spin is going anti-clockwise, blue spin is going clockwise. And what you do is you put a spin flip about this direction. So red comes down, blue goes up, but this is a slow, low frequency noise. It is slowly precessing with the same direction. So direction is not changed. So red keeps on precessing in the anti-clockwise, blue goes in the clockwise. So after time, again, after equal duration of time, they all rephase. So they all come back to the same phase. So this is called Hahn-Echo. So dephasing is cancelled. So dephasing is rephased, and so that is also called as suppression of incoherence. Now, if it is a high frequency noise, you have to do this very, very frequently. So Hahn-Echo you have to do very frequently. That's called the CPMG decoupling. And so there has been a lot of development these days in this. There has been development in terms of how you place these pi pulses and what should be the optimal times and so on. Okay, so now coming to the density matrix again, as I said, there is a decay of the off diagonal elements in the density matrix due to the Z noise. And if you look at that off diagonal element now in the presence of CPMG, so now that sinc function is replaced by some filter function. And this is interesting because now CPMG is in our hand. So we can control the duration, we can control the amplitude and so on. So now can we control the filter function? And it turns out that it has very interesting feature that, so this filter function that moves with the duration of the pi pulse. So if the pi pulses are applied very sparsely, then it is in one place. If it is they are applied very frequently, then they are in the filter function is in another place. So, and also this high, the decay constant. So that is actually the overlap. It is actually overlap of the spectral density, that is the noise spectrum. This is the noise spectrum and the filter function. So by doing experiment at these different pulse spacings and by comparing, by extracting these high values, we can actually get the noise value at these points because it is the overlap is given by this high. So we can get noise spectral density at various frequencies by recording the experiment at different pi pulse durations. So that is very interesting, and it is called as noise spectroscopy, and it is very powerful technique now to understand the color of the noise. So that can be done now in the presence of this space resource. So now we go back to the noon state and do this CPMG experiment. And now what we can do is we can get the noise spectrum for all these coherence orders. For various coherence orders, And now we can find out we can understand the properties of the noise. In fact, there has been, NMR has a long literature on relaxation. And so we could actually verify the prediction of Tang and Pines from 1980, who predicted that in such systems, we get correlated identical spins, we get correlated noise, and that we could verify with this. Okay, so that is the advantage of space resource, and it can be done very efficiently. Another quick example is about diffusion. For example, the whole molecule is now diffusing in the sample, and if you have a gradient field, that's a inhomogeneous field. Now, in the presence of diffusion, it is like a noise. The spin is experiencing Z noise because there is a gradient field and it is diffusing. It is like a Z noise. And now, if you have known state, you can, in fact, very efficiently measure diffusion constant. In fact, here the diffusion delay for normal single quantum diffusion experiment is about 180 milliseconds. And with order of magnitude shorter diffusion delay, you can get the same diffusion curve and extract the diffusion constant. You can also sense XY field. All you have to do is change the basis from Z to X or Y, you can get XY field. So you can sense XY noise or XY fields, XY inhomogeneity just by change of basis. So in this case, we showed how to measure the RF inhomogeneity of the probe coil itself by using moon states. Okay, so that is one example. So coming to this second example, which is very interesting and very useful for quantum information community. So that is called quantum state tomography. So when we do quantum computation, at certain stages, we want to know how is the algorithm progressing, or is there any problem, or is there any improvement that we can do at certain stage of the algorithm. And to do that, we need to know what is the state at that point. So in order to do the state analysis, we have to measure every element of the density matrix. And so if you see, there are 50, if you take 2 qubits, for example, there are 15 real parameters here. So diagonal elements are real. The last diagonal element is fixed by the trace condition, and the rest are complex. So there are 15 unknowns here. And it turns out that in nuclear magnetic resonance, so we can measure all these 4 diagonal off-diagonal elements directly as signal. So they are the direct elements which can be measured in one shot. But the rest of the elements, they are not accessible for direct measurement. Okay. So direct measurement gives these 8 parameters. So they in the form of 8 linear equations. And so in order to solve all the 15 real unknowns, we need at least 2 experiments. In the second experiment, what we do is we apply certain unitary operators, known unitary operator we apply precisely such that part of these inaccessible elements are transferred to accessible elements. Okay. So so you can say these are dark elements. So dark elements are partly converted into the accessible bright elements. So just by doing 2 experiments, you get another 8 linear equations. So 8 plus 8, 16 linear equations, and you can easily solve the 15 real unknowns. So that's the idea of quantum state tomography. So it is something like this. So you have a state which you want to know. So you touch different parts of the object and try to find out what it is, and then solve the linear equation in a consistent way and find out what is the object. So, but then this is not a easy task. It is not a it is not cheap. It is very expensive. The cost grows exponentially. The number of experiments grows exponentially with the number of qubits. Now, one proposal that has come is that if you use additional qubits called ancillary qubits in known state, suppose you have certain number of qubits which are unknown in unknown state, and you want to do quantum state tomography, you add that system with some additional qubits with known state. They are called ancillary qubits. Then what happens is number of observables increases. In each experiment, you can extract more expectation values. Okay. So, but then the state of ancillary qubits is already known. And then what happens is by using this different unitary transformations, you can very efficiently measure the unknown elements. And then, in fact, if you have sufficiently large number of ancillary qubits, you can even make single shot measurement of quantum. You can even achieve single shot reconstruction of quantum state. So that is the Ancilla assisted quantum state tomography, AQST, and so that can be very efficiently carried out. In this case, 2 qubits or 2-qubit quantum state tomography is achieved with the help of 1 additional qubit using just 1 experiment. So that will give you complete density matrix. Now, what interestingly, what happens is, in addition to make it very efficient, you can do it in single shot. It also improves the quantum Fisher information. So by using ancillary qubits, the quantum Fisher information can be amplified by a factor of up to 50. So that is very interesting because so we know that quantum Fisher information and precision, they are inversely related. So the variance is inversely proportional to the quantum Fisher information. And so if you increase the quantum Fisher information by 50, that is a really boost in the precision. And then you can ask, what is the resource that is being exploited in this? And we found that it is really harnessing the quantum discord in the correlated state. So that is the space resource I'm talking about. Okay, so coming to time resource briefly. So let's say we have a quantum system that can live for a long time. And so NMR has been around for last 70 years. And until 2004, we were taught in NMR classes that you have 2 barriers for time. One is T1 and another is T2. So those are the holy barriers. You can't cross those barriers. But in 2004, Malcolm Levitt came up with this idea of using noise resilient subspaces, or something called as long-lived singlet states. So these are the eigenstates of symmetric Hamiltonian minus I1.I2. So what happens is, if you populate singlet state, then somehow you can populate singlet state, then it gets trapped. And this singlet to triplet, this is the triplet subspace, and singlet to triplet the transitions are not allowed by any symmetry preserving processes, because singlet is antisymmetric and all these are symmetric states. So any symmetry preserving process cannot connect these levels. And that's a very powerful way to preserve quantum state, because if you start from thermal equilibrium and prepare the spins in this state, and then it will remain. In fact, you can even take it out of the magnet, because this is spin 0. It doesn't interact with magnetic field per se. So you can go around and have coffee and come back and put it in the magnet and convert back to the observable magnetation and detect. And this is the principle of some of the techniques that Professor Budkar mentioned in MRI. So they use this singlet method. Okay, so it has been shown that they can live up to an hour or even longer. And singlet state NMR is now it's an interesting branch of NMR. And there are many applications, including precision spectroscopy. One example is this. So this is long-lived coherence, slightly different. It is the transition, it is the superposition of these 2 levels. In fact, that is also long-lived. And that is called long-lived coherence. And you can see that normal spectrum of these 2 hydrogens show this J coupling of 5.8 Hertz with a precision of 0.8 Hertz. But if you now check what is the long-lived coherence, so that is the spectrum of long-lived coherence. And so line widths are drastically reduced now, because you can collect signal for about 100 seconds, whereas here it is only 1 second. So that is sustained. The signal sustains for 100 seconds in this long-lived state, long-lived coherence. And the line width greatly reduces. And you can see the precision here now up to by about millihertz. Okay, so that's the advantage. So the precision is greatly enhanced by going to the long-lived coherence. Now, one can ask whether we can combine these two. So whether we can have the correlation large network of spins in a correlated state plus time resource, the long-lived coherence. So that is what we are trying. And these are our initial experiments. Suppose we take isotropic liquid, and in this isotropic liquid, molecules are randomly tumbling, and so there is no dipole-dipole, there is no average dipole-dipole coupling. On the time average, they vanish. There is only indirect coupling via covalent bonds. And so in the case of oriented systems, so you can take liquid crystals or solids, crystals, so they are oriented, molecules are not randomly tumbling. And so we can get the dipole-dipole coupling. Good thing about dipole-dipole coupling is that they are long range. So they can give us more number of correlated spins. So that we can use. However, singlet state was so far demonstrated only in liquids. And so we found perhaps one of the first demonstrations of singlet state in the liquid crystal. So recently we found singlet state in the long-lived singlet state in the liquid crystal phase. So that is interesting. So this is the molecule that we found. So these two hydrogens sustained long-lived singlet state in liquid crystal. This is MBBA. So that's a partially oriented system for a long time. And in fact, it was living such a long time that we could even sustain across the phase transition. So there is a phase transition happening, and we heat the liquid crystal and it goes to isotropic phase. And I'm not aware of many quantum coherences that live across the phase transition. So this is one interesting observation, that the quantum superposition lives across the phase transition. So the system, whole system is undergoing phase transition, but the coherence is still alive. So this is prepared in partially oriented phase and detected in isotropic phase, and we still get the signal. Okay, so I think I have only a couple of minutes left. So let me quickly just mention that there is a new way to do sensing. So that is using time crystals. I know there are skeptics here. Okay, so what we do is there is a temporal, so there is a periodically driven system, and we find that there is a temporal rigidity associated with them. So in this case, we apply the pi pulses periodically. So we go on flipping regularly by applying pi pulses. And normally what one expects is the system is not robust against the errors in the pi pulse. So if the pi pulses are not pi pulse but 10% off, then errors go on building up. But what happens is if it is a time crystal, then it is robust against the errors. So even if the pi pulses are imperfect, the errors don't get added up. They don't build. The effects are not additive. In fact, there is a collective field provided by the many body system that constrains the errors. So that is what provides the temporal rigidity here. And so that's why we call this as a time crystal, and we observed this in this 37 spin system. And we could see the temporal rigidity even up to about 22% error in the pi pulse. Now, more recently, so there is this paper of using time crystals as sensors of AC fields. So this is another example of how one can employ space resource plus time resource as for enhancement of measurement. Okay, so the last thing I wanted to mention is this is an ongoing work. I'll quickly mention in a minute that we can employ weak value amplification in quantum sensing. So what we do is there is a weak interaction between the system and the probe, but the system itself is in a correlated state, and then we do post selection. So this weak measurement and weak interaction and the post selection, these are the two ingredients of weak value amplification, and that can be used for quantum measurement, efficient quantum measurement, and for measuring weak interactions. So some early simulations show that we can get a very nice improvement. This is one simplified example. There is a weak coupling between these two hydrogens, which is not seen in this spectrum at all. So we expected 4 splittings here. Each of these peaks should split into 2. We don't see that because line widths are a couple of hertz. But if we do this experiment, in fact, we are measuring correlated state here. And then we can see that it can be it is actually 1.3 plus or minus 0.2 hertz. So that's a quick example. Okay, so this is a summary of my talk. And so measurement can be enhanced by correlated spin network, which we call as space resource. And by going to long living coherences, that's the time resource, and a combination of them, space and time resources. And let me end with advertising 2 posters by our group. One is by Arijit. So that is on experimental investigations on thermodynamics on complex magnetic fields. And by Vishal, so this is on counter diabatic pulses for singlet state preparation. So please go and have a look at them. Thank you.
Questions?
So what limits the coherence time of the singlet states? You said that it's only 1 hour, right?
Yeah, up to 1 hour. People have demonstrated more than that also, but those are on special systems. Typically, we can get 5 times at least without doing anything, any purification, or 5 times of T1, typically.
And what about the solid state? Like, is it possible to have singlet states, long-lived singlet states?
Yes, so this is
solid state
hinting,
also?
yeah, that would be very interesting. Actually, that is what we want to look at. If you can find singlet states, long-lived singlet states in NV center, that would be great. So, so it would be interesting.
Okay, thank you.
Yeah. So I'm trying to understand. So you said that this, as you go through this phase transition, your correlation, so the superposition survives.
Yes.
So if I compare with classical sort of phase transitions, given the temperature, so I think if I understand correctly, the correlation length diverges, right, near a phase transition. Like things become very slow. So I would say, so everything sort of in some sense becomes correlated.
So here,
I'm just trying to understand why is it surface?
Maybe let me clarify. So spins live in the Hilbert space.
I understand.
Yeah, and the sample is undergoing phase transition from liquid crystal phase to liquid phase. Okay.
Yeah.
And during that time, a lot of things happen, like turbulence and environment, noise, everything. So ordinary states, ordinary superpositions don't live across the phase transition. At least I have not seen. Okay. But long-lived singlet state are immune to noise, such kind of disturbances. And it so happens that it outlives this phase transition period.
Yeah, so it's related to this question, this slide. So it seems like your magnetization still has a decay. So when you're talking of rigidity, like what do you mean exactly?
So, so with respect to errors, so here errors are increased. Okay. Now, if you, for example, you can do 2 things. Okay. Now I can decouple these. I have that result. Actually, it's there in this paper. Okay. So if you decouple these, then it dies very fast. So then you start seeing sidebands immediately. So that means this is a collective phenomena. So there is a many body effect here. If it is only silicon, this is the silicon magnetization. If it is only silicon, then it cannot sustain that errors. It cannot oscillate in the presence of errors. So there will be actually beat pattern. So there will be interference pattern and you will get sidebands immediately. With the 0.1, you will get strong sidebands. But in the presence of these hydrogens, interactions with hydrogens, okay, so then there is that additional field, okay, so that limits the errors, propagation of errors. Okay. So it can sustain this oscillation for a long time.
So there is a subharmonic, that's a time crystal phase.
Correct.
And what is the other phase it melts down to? That's a randomized phase? Or
Yeah.
like kind of a gas
Yeah,
phase?
randomized. It's in NMR, it is oscillatory and slowly randomized. Yeah.
That is no more questions. Thank you.
Thank you. Yeah.